All right, so I'm going to prove proof 2.1, which is the proof that argues that if we are dealing with a closed subspace of Hilbert space, so let's call our closed subspace M, and our Hilbert space we're going to call big X. So let little x be a member of the Hilbert space, and let M sub 0 be the vector in our subspace M that is the closest vector to X. What we need to do is to prove that M sub 0 exists, and that X minus M sub 0 is orthogonal to M. So how do we prove this? Well, actually, I will note that the x minus m sub 0 is orthogonal to m. That's actually part of the proof that we're not going to cover since it's kind of written before proof 2.1 and it's not explicitly included. So I'm just going to focus on demonstrating that this m sub 0 is the closest vector to x and that it does exist. So what we're going to do is we're first going to let delta be equal to the infimum over all of our subspace M of the norm between X and M. And what we're going to do is we're going to construct a sequence of M sub i's such that the limit of this sequence, when we take the norm, the distance from X, it's equal to delta. Now what we want to do is that this infimum is really, we can express it as kind of a minimization problem, and that the M sub 0 that minimizes it does exist. And so to do this, we take advantage of the fact that we are working in X, which is a Hilbert space, and so the parallelogram law holds when we're dealing with norms. And so I have written down here the parallelogram law. So these are the two outside edges of our parallelogram, and we know that 2 times the square of the outside edge plus 2 times the square of the other outside edge, the length of those edges, is equal to the length of the square diagonals. And here, this term is just reflecting the fact that we're only dealing with half of the length of one of the inside diagonals, so we have to multiply that by 2, then the whole thing is getting squared. So just doing some basic algebra, this is what we get. Now, we know on the right-hand side here that because we're dealing with a closed subspace, mi plus mj divided by 2, that's also a member of M. And since we've assumed here that kind of the smallest distance that exists between X and any element of our set big M, any element of our closed subspace big M, has to be in there, we know that it must be the case that this this whole thing must be greater than this number here, because this is the infimum, this is the smallest value that's possible by assumption. And then we also know that we have defined these terms on the right as being elements of our sequence, and we can choose some subscript number, some index large enough such that it's the case that both of these norms are, squared norms I should say, are greater than delta squared plus epsilon squared over 4. And again, doing all that algebra, we end up getting that epsilon squared is greater than, and that should actually be strictly greater than mi minus mj, the norm squared. So we've shown by doing that m sub I, the sequence, is Cauchy. And because the sequence is a member of X, which is a Hilbert space, we know that it also converges. So we're going to call that convergent point m sub 0. And furthermore, because our sequence is in M and we specify that M is closed, we know that m sub 0 is also an element of M. So we've shown that, this minimum norm exists. Now, how do we then say that actually, so we've demonstrated that this norm exists. Now we need to show that it also minimizes the distance. And so we can argue that this limit point, m sub 0, converges to this here. So when we take the norm, that we have this convergence happening by the continuity of the inner product. And so in that case, we have that if we take the limit of x minus m sub I as I goes to infinity, we end up getting x minus m sub 0. And so as we've mentioned before, this is what we defined. We know it's equal to this because of the continuity of the inner product. And we define this sequence as the one which approaches its limit point is equal to the infimum, which is delta. So that is proof 2.1.